Thank you. I decided to talk about this. This was the subject of the PhD thesis of a student of mine, supervised jointly with Christian Bonatti. So the student's name is João Carnevale. Well, finished last October, and unfortunately, well, he did this PhD during COVID, and I think didn't really like the becoming a mathematician. So he did really a wonderful work. I'm so happy to talk about his work, but well, I don't know if we'll be keep working in research in the next years. No idea. Anyhow, I think it's good to advertise his work because it's really worthwhile. So let me give you the main setting, the general setting. I like to study groups acting on spaces. Well, usually they are one-dimensional spaces. So you have a group G acting on X, and you don't know G, what G is, but you put assumptions on the dynamics of single elements in G. So you want to say every non-trivial element is acting in a simple way. You want to fix. So as you see by the title, you want to say that every non-trivial element is acting with at most n fixed points on the circle. Is the kind of assumption. Then you want to draw a conclusion on the group G, on the algebraic structure of the group G. So the first example is Hölder theorem. It goes back to 1901 about actions on the line. The time wasn't stated like that. Is that if G acts on the line by order preserving homomorphism freely, then there exists a map phi from G R seen as the group of translations, which is actually coming from a semi-conjugacy of the action. This is a homomorphism coming from a semi-conjugacy of the action to an action by translations. And this homomorphism, moreover, is injective. Okay. You have your group acting on the line, then you have a group of translations, and you have a map H, which is surjective and which is equivalent for the two actions, and you have a map this pi. This is one of the basic theorems for the first theorem, the theory of groups acting on the line. Let me stress that if you want to go, well, with this, you can also prove the analog statement for actions on the circle. Okay, so this is easy to deduce that if you have an action of G on the circle, which is free, then you have G is actually a group of rotations. The same conclusion. Yes. Yeah. Okay. So if you want to go to higher dimension, the situation is very more complicated. Here, what it works is that if you have an element with no fixed points acting on the line, then you know what the element is up to conjugacy is translation by 1 or translation by -1. Every single element is conjugate to a translation. If you have an element with acting on the line without fixed points, that's what the element is doing. The same thing here. If you have an element acting on the circle without fixed points, then you know it will be semi-conjugate to a rotation. And so let me put this here. So in dimension 2, if let me call it G, if you have a planar homomorphism, there is a free planar homeo, nothing without fixed points, then this is what is called the Brouwer homomorphism. Okay. Which means that there is a foliation of the plane by lines, which is preserved. And G is acting as a translation along any length of the foliation. Okay. G is translating along leaves. So this means that actually, well, says free planar homomorphism are kind of understood, but they're actually really complex because foliation can be whatever thing you want. And you can put like RIP components inside your foliations, and you can make them accumulate one onto the other. Then you can make things. So the element G is acting as a translation along any length, and the picture can get kind of complicated. Also, the point is that the foliation is not unique. So there is no canonical object associated to the Brouwer homomorphism. And there are really few works about groups acting on the plane freely. The analog of Hölder theorem dimension 2, there is basically nothing known. I think 2 works by Leroux. Well. Results basically by Leroux. And there are about 1 billion groups for the Klein battle group, basically. And nothing more. I think this will be like a nice research project to understand this kind of groups acting freely on the plane. All right. Well, but this kind of justification for myself just to restrict the attention to dimension 1. Dimension 2 is way too difficult. What we can do is consider more, increase the number of fixed points. The next step is consider groups such that any non-trivial element has at most one fixed point. Now, assume, so this is a theorem by Solodov. This is 91. Assume G acts on the line with at most one fixed point. By this, I mean any non-trivial element has at most one fixed point. Then basically what you get is all the examples you could expect. And in this case, the free action case, the reference example was the action by translations. And in this case, the reference example is action by affine transformations of the real line. And that's what you get. So then either there exists a global fixed point, call it fixed point, call it P on the line, in which case what you get is that this point is fixed and the action on the two sides are free. Right? So you get two actions on the three actions on the line, and then you use Hölder theorem. Or there exists a map that would be considered this is phi G to the group of affine transformation of the real line coming from a semi-conjugacy of the action. And this is injective. I was telling you that there are no surprising examples when you go to n equal 1. Let me say the first result from the thesis of João. So now assume G acts on the line with at most two fixed points. Then nothing new. What do I mean by that? Is that what you can do is that well, you have to consider different cases now. You can have two global fixed points, and then you are acting freely on each connected component of the complement. Or you can have one fixed point, and one of the two, on one of the two sides, you will show that the action is free on one side, and free, and this could be affine. Or what you basically get is that there will be or is either, or what you get is affine action. Basically saying that if you put the bound 2 as a bound, well, basically you have 1 as a bound for the non-trivial cases. And question is, can you get different behavior for n starting from 3. I think there is a result by Akhmedov of using work of Akhmedov, telling you that if the action is by diffeomorphism of the interval, like C1 or more regular, something like that. I mean, if you put some regularity assumption, the conclusion is that you can get anything new. So the question is for actions by homeomorphism on the line. So this was his first result. Actually, it was done during his master's thesis. And so then his work was more focusing on actions on the circle. So the idea so far is that we have some reference actions. The first case was actions by translations. The second case was action by affine transformations. And dimension 1, the next geometry you want to consider is projective geometry, actions on the circle. So, if you want to be formal, you look at the group of homomorphism of the real line or homomorphism of the circle, and you're asking yourself, what are the Lie groups inside these groups, connected Lie groups? And then basically you have the group of rotations, you have the group of affine transformations, and you have the PSL2 of R and all the central extensions of PSL2 of R. Okay. It will be like. When you look at PSL2 of R, this is acting on RP1 that you identify with the circle. And this action has at most 2 fixed points. And well, just to give more examples, you can also consider lift. Right? So what you have, you have PSL2 of R right here, and you can lift the circle k times, and you have a k-fold central extension. And this is still a circle. And we are lifting, we are taking the k-fold lift. If you have 2 fixed points downstairs, then you get at most 2k fixed points upstairs. So in this case, this is, you can take a color. So one naive guess would be, I consider a group acting on the circle with at most 2 fixed points, then we'll guess that the action is semi-conjugate to an action by projective transformations. But this is a naive guess because well, this action has this property at most 2 fixed points, but it has more, it's more restrictive, because if you have a Möbius transformation of the circle of the projective real line, then if you look at the two fixed points, one is associated with eigenvalue, which is larger than 1, and the other one is associated with an eigenvalue, which is smaller than 1. And one fixed point is attractive, and the other one is repelling. Okay. So any element. Okay. So if you have a transformation, projective transformation of the circle has two fixed points, then it is of north-south dynamics. It is hyperbolic. Means that you have two fixed points. Dynamic is that one point is an attractor and the other one is a repeller. So let me say group G at the end of the circle is Möbius-like if any element is individually conjugate or semi-conjugate. Okay, is either elliptic, there's no fixed point, and then you want hyperbolic, which is this picture, or parabolic. Which means one fixed point, and the dynamic is the one coming from, like, you remove the point and then you get the translation. So I'm putting this condition because you can easily violate this condition. You take an action of G, so G is generated by one single element, like G, where G has two fixed points, but the dynamics is incoherent with this picture. So you have two parabolic fixed points. This is not an hyperbolic element. So somehow you, okay, say first naive guess, if I'm just considering groups acting on the circle with at most two fixed points, then I can easily produce examples of groups which are not here in PSL2. Yeah. If I see, okay, good question. Yeah, I come to that. Okay. Yeah. But and so the question then would be, okay, let me put also the restriction that my group is Möbius-like. This is enough to like give a dynamical characterization of action of subgroups of PSL2 of R. The answer is no. There were constructions, examples by a student of Gabay in the 90s, of Kovačević. So there should be like something like that. There should be some accent. Say examples of Möbius-like groups not coming from PSL2. And so the PhD thesis of João Carnevale was kind of giving a structured theory of these examples of Kovačević. Well, he proved also other results. Okay, now I have to raise the blackboard. Yeah, I'm going to that. Yeah, I need for blackboard. This. Now, this is kind of conjecture. Yeah. Then, well, unfortunately, yeah, COVID was bad for him, and so he wasn't really interested in going on with this project. But I think it was kind of close. And so, one, okay. So, what is the idea for this? Okay, let me give first one result. So this is something we, yeah, Bonatti. And myself. So there is a preprint on the archive about this. This is kind of first result. Let G be a group of homomorphism of the circle, if at most n fixed points. I want to put non-elementary just to avoid that kind of example over there. So no invariant probability measure. Also put here, which is non-discrete in omeo class with respect to the C0 topology. Then actually, so this non-discrete, you want to look at the closure of the group. Then G closure, G bar, is conjugate one of the Lie groups over there. Okay. Let me say, if you want to produce an example, you have to consider groups which are discrete. Here you have to put no. You prove that the action if it is non-discrete, the action is minimal. And well, it is. So how do you produce the examples? You want to start with something you know, like subgroups of PSL2 of R, then you want to combine two different actions, like making surgeries. Okay. Surgery. Or I mean, you want to combine things. It's like in hyperbolic geometry, what you would like to do is that you have two surfaces with boundary you want to glue them together. And if you think in terms of fundamental groups, when you look at the cover, you have one which is acting with some limit set. And then you take another one which is acting with another limit set. And what you want to do is that you want to put lambda prime, you want to consider a new circle where you see one limit set on one side and the other limit set on the other side. And if you want to, maybe there should be 4. And if you want this to glue to an action of a closed surface group, you want to say something about the stabilizer. You want them to match. This is the idea in hyperbolic geometry. And Kovačević example is doing that, but to create something which is not in PSL2 of R. So let's explain this. Basically, what you want to do, you want to define like a combination of two actions on the circle, or amalgam, or something like that. So you have two groups acting. You have G and H. And you choose, say, one point. Here, this is X. Take another point, Y. Then what you want to do, you want to open this point to blow up the orbit of this point. So you blow up the action. What you do is that you insert some interval I and some other interval here, J. And then if you have another point which is in the same orbit, G dot X, then you have another interval for IG. And you have to define the action of the group G on this interval I, and then you have to replicate the action of the group G inside the interval IG by considering like the conjugating what the group is doing on this interval I by the element G. This is a blow-up construction. And so what you do is that once you open this this orbit, you take your two intervals I and J, and you put the complement of J inside I. Then you create a new circle. Now, so here you have your big, large interval I, and here you have like the complement one, but when you open up, you have some limit set, lambda prime, and the same here. And so you put like lambda prime on this side, and you put lambda on the other side. And what do you need to make this construction work? Well, this is fine if the stabilizers of these 2 points are isomorphic. You want to choose these 2 points. With isomorphic stabilizer, and the choice of an isomorphism is a parameter of this combination construction. So this is isomorphic to some S. And basically what you get at the end by the ping pong lemma is an action of the amalgamated free product over S of the two groups on the circle. There are many ways of making this surgery of action, but the point is that you can show that once you, if you make this action to be minimal, if you look at the semi-conjugacy class of the action, then there is a unique way up to conjugacy. So this object is well defined. And we call this like the amalgamated free product of actions on the circle with respect to the many parameters. So you can do this with one orbit. You can take a finite number of orbits satisfying some parameter. You can do this. Now, just to make to give one example, assume that your group G is non-discrete in PSL2 of R. Take when you have a non-discrete, non-elementary, it doesn't matter of this. When you have a non-discrete subgroup of PSL2 of R, then by a classical result, you know that there is an element without fixed points, an element which is an elliptic element, which is conjugate to an irrational rotation. Up to conjugacy. So the group is in PSL2 of R. So any element has, any non-trivial element has at most two fixed points. So there are, if you remove a countable collection of points, you have points with free stabilizer. So you can take a point with trivial stabilizer, and you take this point as X. And so now if you, then actually you can take even two of them, oh, that's fine. So if you look now at the picture, over there, if you look at the element so you have this rotation, G, it will be no longer a rotation. It will be semi-conjugate to rotation, but it will have an invariant counter set, the orange part. Okay. So the new G, the resulting G, has no fixed point. And the irrational rotation number. Oh. So sorry, so irrational rotation number and an invariant counter set. If you look at what this is doing, if you take some sufficiently large power, so if it has some irrational rotation number alpha, then you take G to some Qn, where Qn are the denominators of rational approximation of alpha. if you describe the graph of this element, it will be something like a Davis staircase without fixed points. It's going to be close to this picture, where the jumps are at the counter set. And so why is this giving a contradiction? So this violates the so-called convergence property. So this is one of the deepest results on groups acting on the circle. How can you give a dynamical characterization of subgroups of PSL2 of R? So this is so you have this term by Tukia, then extended by Gabay and Kasson-Jungreis. Telling you that G acting on the circle is conjugate into PSL2 of R if and only if G satisfies the convergence property. So what is this? That means that if you, what is this? So for any sequence Gn in G of distinct elements, you can extract G and K converging from some north-south map. So if you look at the graph, it will be something like this thing. So, or you have that Gn is equicontinuous. So this is one of the most important results in the groups acting on the circle. It gives the dynamical characterization of PSL2 of R, but with respect to the original question I was asking at the beginning, so if I put restriction on elements, can you say something about the group? This is kind of a global condition. It's something about any sequence of elements inside the group. It's not just about single elements. Okay, so this element is violating this convergence property because this sequence is converging to a Davis staircase, which is not allowed. So this is how you prove that it is not conjugate to a subgroup of PSL2 of R. And the second thing you want to prove is that the amalgamated product still has the property that every non-trivial element has at most 2 fixed points. And this is something there is also, I don't have time for this, I'm running out of time, sorry for that. So João Carnevale proved that when you make an amalgam of actions with 2 groups, so that any of the group has at most n fixed points, then the resulting amalgam will still have this property. You don't increase the number, the bound of the number of fixed points. Actually, what he proved is that, well, if moreover you put some restriction on the combinatorics of the way you are doing your amalgam, you just select one point, there is no restriction. And if you take any element which is not conjugate, which is not in a vertex group, that will be hyperbolic with one attraction Borel pair. I mean, this is one of the main results this thesis. And thanks for your attention.